Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the essay. The year 1930 witnessed the publication of a scientific paper currently etched into the annals of history, a momentous contribution titled A New Type of Nuclear Reaction, authored by Otto, Hahn and Lise Meitner. This essay undertakes a comprehensive evaluation of this seminal work, meticulously examining its assertions, methodologies, and conclusions. Our focus rests predominantly on a detailed examination of the internal arguments presented within the paper, assessing their validity, coherence, and impact within the scientific landscape of the era. Emphasis was placed on the specifics of the experimental design, data interpretation, and theoretical framework proposed by Hahn and Meitner, considering contextual relevance only insofar as it illuminates the intrinsic merits and limitations of their Section 1 Introduction and Initial Hypothesis Presentation. The paper opens with a concise overview of existing research concerning the bombardment of uranium with neutrons. Prior investigations, primarily conducted by Enrico Fermi and his team in Rome, had suggested the creation of transuranic elements beyond uranium in the periodic table. Hahn and Meitner's initial hypothesis clearly posited that the bombardment of uranium with neutrons produced a series of radioactive isotopes, some of which exhibited properties dissimilar to those previously identified. A critical assessment of this introductory section reveals the importance of building upon existing scientific paradigms. The notion of transuranic elements, while revolutionary, rested upon specific interpretations of experimental data involving the analysis of decay products emanating from neutron-irradiated uranium. The introduction lays the groundwork for a rigorous exploration of these decay products, setting the stage for a systematic examination of their chemical and physical characteristics. The authors implicitly acknowledge the prevailing scientific consensus, while simultaneously hinting at the possibility of alternative explanations, thus establishing a suitable degree of scientific skepticism. Section 2 Experimental Setup and Irradiation Procedures. Describing the experimental setup forms a substantial part of the 1938 publication. Hahn and Meitner painstakingly detail the methods employed to irradiate uranium samples with neutrons. They describe the usage of a neutron source, often radium mixed with beryllium, to generate the particle bombardment necessary to transform uranium. The authors meticulously explain the chemical separation techniques used to isolate and analyze the resulting radioactive isotopes. This involved precipitation with carrier substances, such as barium chloride, followed by fractional crystallization to purify the newly formed elements. Evaluating this section reveals the meticulous nature of the experimenters. A methodology was characterized by exacting chemical separations and careful measurements of radioactive decay properties. However, potential limitation lies in the reliance on carrier precipitation, a technique susceptible to co-precipitation, where unwanted substances are inadvertently carried along during precipitation, which would render the results invalid. The authors, to their credit, acknowledge this possibility and assert that they have taken steps to minimize its impact and ensure the accuracy of their results. One could argue that the absence of more sophisticated analytical techniques readily available today represents a constraint on the conclusions they could convincingly. Section 3 The Identification of Barium Isotopes. One of the most consequential claims presented within the paper involves the identification of barium isotopes as products of uranium fission. Hahn and Meitner meticulously described their chemical analyses, which demonstrated that certain radioactive isotopes, initially assumed to be transuranic elements, displayed chemical properties indistinguishable from barium. This identification was based on a series of definitive chemical separations and comparative analyses with known barium standards. A close examination of this claim reveals a revolutionary departure from established scientific paradigms. The idea that uranium, An element with a high atomic mass could split into smaller elements such as barium was entirely unexpected and contradicted existing theories of nuclear physics. The authors confront this apparent contradiction head-on, acknowledging the surprising nature of their findings and emphasizing the need for further investigation. The evidence presented, while compelling, relies entirely on chemical identification, which some contemporaries may have viewed as inadequate. The lack of direct physical measurements of the barium isotopes, such as mass spectrometry, could be perceived as a potential weakness in their argumentation. Nevertheless, the meticulous nature of their chemical analyses and the consistency of their results lend significant weight to their claim. Section 4 Explanation of the fission process. The 1958 paper offers an initial attempt at explaining the observed nuclear reaction. Hahn and Meitner propose, somewhat tentatively, that the uranium nucleus, upon absorbing a neutron, undergoes a process of fission, splitting into two smaller nuclei, along with the emission of additional neutrons and energy. They propose that this process accounts for the observed formation of barium isotopes, as well as other lighter elements. Evaluating this section requires recognition of the theoretical limitations prevailing at the time. The liquid drop model of the nucleus, while offering a conceptual framework for understanding nuclear stability, lacked the sophistication to fully explain the dynamics of fission. Hahn and Meitner's explanation, therefore, remains somewhat qualitative, lacking a quantitative theoretical treatment of the fission process. The authors appropriately acknowledge this limitation, recognizing that a more detailed theoretical understanding is needed to fully elucidate the observed phenomena. It is worth emphasizing that the paper emphasizes description and experimental results, rather than a full theory that explains the exact theoretical underpinnings. This approach, while cautious, reflects the preliminary nature of their understanding and the need for further research to validate their proposed mechanism. Section 5 Discussion of energy liberation. The paper discusses the implications of the fission process with regard to energy liberation. Hahn and Meitner hypothesize that the splitting of the uranium nucleus releases a substantial amount of energy consistent with Einstein's mass energy equivalence principle, expressed by the equation energy equals mass times the speed of light squared. They suggest that this energy accounts for the observed kinetic energy of the fission fragments and the emission of gamma radiation. Critically examining this section reveals the profound implications of their findings. The realization that nuclear fission could liberate substantial amounts of energy opened up entirely new avenues for scientific exploration and technological development. Hahn and Meitner correctly identify the connection between mass defect and energy release, although they do not provide a detailed quantitative calculation of the energy involved. The absence of such a detailed calculation may be attributed to the limited availability of accurate nuclear mass data at the time and a lack of full understanding of the fission products. Nevertheless, the qualitative discussion of energy liberation serves to highlight the potential significance of their discovery and to motivate further research into its implications. Section 6 Consideration of alternative explanations. Acknowledging the novelty and potential implications of their findings, Hahn and Meitner explore alternative explanations for the observed formation of barium isotopes. They consider the possibility that the barium is not a direct product of uranium fission, but rather arises from some other unknown nuclear reaction involving previously unidentified transuranic elements. Upon carefully evaluating these alternative explanations, they conclude that they are less plausible than the hypothesis of uranium fission. This section underscores the scientific rigor employed during the work by explicitly acknowledging alternative explanations and systematically evaluating their plausibility. Hahn and Meitner demonstrate their commitment to objectivity and their willingness to consider alternative interpretations of their data. Their rejection of alternative explanations is not based on dogmatic adherence to their initial hypothesis, but rather through careful comparison of the available evidence and assessment of the relative likelihood of different scenarios. This approach strengthens the credibility of their conclusions and reinforces the impression of intellectual honesty. Section 7 Examination of other fission products. Beyond identifying barium isotopes, the paper alludes to the existence of other fission products resulting from the neutron bombardment of uranium. Hahn and Meitner mention the observation of radioactive isotopes with chemical properties indicative of strontium and other lighter elements. While they do not provide as detailed a characterization of these other fission products as they do of barium, their preliminary identification provides further support for the fission hypothesis. Assessing this aspect of the paper reveals an awareness of the complexity of the fission process. The authors recognize that the splitting of the uranium nucleus likely results in a spectrum of fission products, each possessing unique chemical and physical characteristics. Their preliminary identification of strontium and other elements indicates that they were actively investigating the full range of products resulting from the fission reaction. The omission of detailed characterization of these other fission products, however, suggests that their primary focus remained on confirming the formation of barium and establishing the fundamental mechanism of uranium fission. Further study would be needed to characterize the entire spectrum of fission products and to understand their relative abundances. Section 8 Discussion of the role of Lise Meitner. It is imperative to acknowledge the crucial role of Lise Meitner in the research process. Although the paper bears only Otto Hahn's name, Meitner's contributions were significant. The collaborative nature of their partnership, which had lasted many years, ensured that Meitner's expertise in nuclear physics informed every aspect of the experimental design, data analysis, and interpretation of results. This section is designed to emphasize Meitner's scientific influence. The historical context is critical. The persecution of Jewish scientists in Nazi Germany forced Meitner to flee the country. Prior to the publication of the paper, the omission of her name from the publication was, therefore, a consequence of political circumstances, not an accurate reflection of her scientific contribution. The erasure of Meitner's contribution represents a deep ethical failing, reminding us of the profound impact of political forces on the scientific enterprise. Subsequent historical scholarship has helped to restore Meitner's rightful place in the discovery of nuclear fission, highlighting the injustice of her exclusion from the 1944 Nobel Prize in Chemistry, awarded solely to Otto. Section 9 Contemporary Reception and Validation. The publication of a new type of nuclear reaction generated immediate and widespread interest within the scientific community. Physicists and chemists around the world quickly recognized the significance of Hahn and Meitner's discovery and began conducting experiments to confirm their findings. These independent investigations provided crucial validation of the fission hypothesis. Evaluation of the paper's contemporary reception reveals the transformative impact of the work. The confirmation of uranium fission by other research groups lent strong support to the initial claims presented by Hahn and Meitner. Physicists such as Niels Bohr and Enrico Fermi were quick to appreciate the implications of fission for nuclear physics and potential applications. The swift validation of the discovery underscored the meticulous nature of the original research and the clarity with which the results were presented. However, the initial interpretation of the results was not without its challenges. The theoretical understanding of the fission process required further refinement, and scientists continued to grapple with the complex dynamics of nuclear reactions. Section 10 Subsequent Research and Developments. The discovery of nuclear fission opened the door to a flood of subsequent research and development within the field of nuclear physics. Scientists quickly realized that the fission process released additional neutrons, creating the possibility of a self-sustaining chain reaction. This realization led to the development of nuclear reactors and, ultimately, nuclear weapons. This contextualization frames the significance. The subsequent research stemming from Hahn and Meitner's work dramatically reshaped the landscape of scientific and technological progress. The development of nuclear reactors provided a new source of energy, while the creation of nuclear weapons introduced both immense power and profound ethical challenges. The discovery of fission also spurred further research into the fundamental properties of the atomic nucleus, leading to new insights into nuclear structure and nuclear forces. The legacy of this discovery is therefore multifaceted, encompassing both positive advancements in energy production and medical applications, as well as the enduring threat of nuclear proliferation. Section 11 Ethical Implications and Societal Impact. The discovery of nuclear fission and its subsequent applications have raised profound ethical questions and had a transformative impact on society. The development of nuclear weapons, in particular, has created an era of unprecedented global insecurity and moral responsibility. Exploration of the ethical and societal implications remains imperative to understanding the full ramifications of the work. The use of fission to create devastating weaponry has had a lasting impact on the relationship between science and society, leading to increased scrutiny of scientific research and a greater awareness of the potential consequences of technological advancements. The development of nuclear energy, while offering a cleaner alternative to fossil fuels, has also raised concerns about nuclear safety and the disposal of radioactive waste. The legacy of this discovery, therefore, encompasses both the immense benefits and the potential harms associated with nuclear technology, underscoring the importance of ethical decision-making and responsible stewardship of scientific knowledge. Section 12 Assessment of Enduring Significance. In conclusion, the 1958 paper A New Type of Nuclear Reaction represents a watershed moment in the history of science. Hahn and Meitner's meticulous experimentation and insightful analysis led to the discovery of nuclear fission, a phenomenon with far-reaching consequences for both science and society. The enduring significance of the work lies not only in its scientific accuracy, but also in its transformative impact on the world. Even with the benefit of hindsight and modern equipment, a carefully constructed arguments and experimental observations leading to the hypothesis of division of the uranium nucleus remain valid. The recognition of barium involved ingenious methodological steps in a radiochemical procedure. The discovery paved the way for entirely new avenues of investigation, ultimately leading to the development of nuclear energy, nuclear weapons, and new insights into the fundamental nature of matter. While the ethical implications of these developments remain complex and debated, the scientific achievement itself stands as a testament to the power of human curiosity and the relentless pursuit of knowledge. The very specific claims made within the paper relating to the actual physical experiments were ultimately proven correct, thereby validating the scientific merit. The implications, as discussed in the latter sections, speak for themselves.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.